important anyway. Sorry we missed the first 6 slides. Okay, so the urinary system is a pretty simple system in terms of the number of organs involved. It's simply 2 kidneys down in your back of your belly. They are retroperitoneal. Remember, they live behind the peritoneal cavity. There's two kidneys, and then each kidney has a tube coming out of it called a ureter that carries the urine down to your bladder. And then you've got a bladder down here, and then the bladder connects to the outside through a tube called the urethra. The urethra is a really simple and very short tube in a woman, probably about 1 inch long, from the neck of the bladder to the outside. In a male, it can be, 14 inches long, guys? Just kidding. It's usually about 4. But anyway, it goes all the way out through the penis. The difference in the male and female, and we'll discuss this, is that the urethra only has one function in females, and that's to carry urine. Whereas in the male, it not only carries urine, but it carries semen, carries the reproductive system as well. So there are some differences there. We'll talk about it. What are the functions of the urinary system? These are pretty straightforward, but yet pretty important. One is that our kidneys regulate our blood volume and our blood pressure. In other words, our kidneys decide if we have enough blood in us or if we have enough blood volume in us. And if we have too much, then the kidney senses that and the kidney starts making more urine and to bring it down. And if we don't have enough, then the kidney will hold on to our water and hold on to our salt and increase our amount of volume. For example, if we had been bleeding and lost some blood, we would be making very little urine. So not only does it adjust the amount of water lost, but it also releases erythropoietin and renin. These are 2 hormones that we'll learn a lot about. Erythropoietin, I think we've already talked about it, known by the initials EPO. It's the major performance-enhancing drug used by the long-distance runners and the bicyclists that need lots of hemoglobin, lots of blood to carry lots of oxygen so they can exercise and do the crazy things they do for 8 or 10 hours a day. So we'll learn about erythropoietin. Renin is another hormone that controls the volume and the salt levels. It regulates our plasma ion concentration. We've already talked about a number of these before, and we're going to touch on them again. Calcium levels. Remember our calcium levels we have osteoblasts, which make more bone, so they suck calcium out of our bloodstream and turn it into bone, make more bone. We have osteoclasts. Remember those ones that have multinuclei and eat up bone? So if our calcium level is too low, the osteoclasts eat up the bone, and that releases the calcium into the bloodstream and makes our calcium level go up. Our sodium, potassium, and chloride, that's basically salt water, right? Sodium chloride and then potassium chloride are controlled in our kidney, and we have lots of controls on that we will talk about. In addition to deciding how much salt to let go, the body decides on how much acid to let go. So we control our pH through our urine. Now that's not the only way we control our our pH. What's the main way we control our pH? Breathing, right. So if we hyperventilate, what happens to our pH? We blow off our PCO2 and our pH goes up, right? We become alkali. And if we're not breathing enough and we're in cardiac arrest or something, for example, and we're not breathing, having an arrest, then what happens to our PCO2. It builds up very quickly. We become hypercapnic, and we become very acidotic very quickly. So when you get called to that code, one of the first drugs you're probably going to be giving is soda bicarb, which is pure bicarbonate, in order to try to bring the patient's pH up from the acid levels to get them normal, to try to get their heart going and so forth. So pH is very much regulated by our kidney. Now, whereas our breathing, we can change our pH in about a minute and a half by either breathing too much or not breathing enough. Our kidney is just as important, but it's a much slower thing. So our kidney kind of fine-tunes our pH. We conserve valuable nutrients. We've got to get rid of all these waste products that our body creates. We talked about urea the other day. The breakdown product of ammonium gets turned into urea. Urea is water soluble, so we can pee urea out. And that's one of the things we've got to get rid of. There's other things we don't want to get rid of. We don't want to pee out sugar, for example. But if our blood sugar levels are too high, if we were diabetic, for example, then we might be peeing out sugar, and that's probably not good, although it might be a great way to go on a diet and lose weight. If you're losing a lot of sugar, it's not a healthy thing. So, I think this line here can be, explained further by simply saying that our kidney decides what we want to lose and what we don't want to lose. We clearly don't want to lose proteins. We clearly don't want to lose sugar. But there's other things we definitely want to get rid of. And that's part of step number 5 down here, detoxifying poisons. Most poisons, we pee them out. We excrete them through our kidneys. And although the liver tends to break a lot of things down to get rid of them, if they're poisonous and we don't want them in our body, certainly the kidney does a lot of that too. Kidneys are located on either side of the vertebral column. The left kidney is a little bit higher than the right. Why do you think? Because there's this big organ over here on the right side which pushes it down, and it's called the liver. Yeah. On top of each kidney is an adrenal gland. We used to call them adrenal glands because they made adrenaline. We call them suprarenal glands, which just means above the renal on both sides. They do a lot of things for us besides make adrenaline. They just sort of, there's no real ligaments or anything that hold them there. It's just all the tissues around them kind of hold them in place. The kidney is protected very much because of where it lives way back deep down inside of you, which is a good thing, because if the kidney was laying right out front, you could ever get punched. Most of the time you'd probably bleed to death from it, but because it's way back in the back, hidden back there along either side of the vertebral column, way back in here, and the rib cage is protecting a lot of it in behind. They're in a pretty protected position. We'll look at the kidney under the microscope. It's got a fibrous capsule on the outside, which covers the whole thing. There's a little perinephric fat capsule that's around it. Perinephric just means around the kidney, nephric kidney. And then there's some fascia back there, which once again isn't really, it's not an anatomic deal, but it helps hold it into place. Here's what they look like from the back. The one on this side here, this is the left kidney. You see it's a little bit higher than the one on the right, but that's totally insignificant, really. Here's the 2 floating ribs. You remember the floating ribs, 11 and 12, don't attach to anything. You can, in fact, I was doing this with the 231 class this morning, having them lean over and try to feel the tips of their 2 floating ribs down there at the bottom. Obviously, the 2 biggest blood vessels in your body run right between the kidneys, the aorta right here, and the vena cava carrying blood back to the heart. The renal arteries are huge, and they bleed like crazy if they ever get torn. Indeed, our kidneys get about 20 to 25% of our total body's blood flow goes through our kidneys. Here's a cross-sectional view, like you'd see with a CAT scan more than likely. This is the left side because here's the spleen, here's the stomach, here's the lesser omentum, remember that. Here's the kidney back here, a renal artery going in, renal vein coming out, and the ureter is below this picture. Nice picture here. If you remember back to 232, we have 3 arteries that come off of the aorta that are unpaired, come off in the middle. The first one right here is called the celiac trunk, and remember it supplies the stomach and the spleen and the liver and mostly that's what it is, those 3 big organs from the celiac trunk right there. The next one is called the superior mesenteric artery, and it supplies virtually the whole small intestine. That was the one I talked about the other day, twisting in Jack Newman and causing the death of most of his bowel. The third one down here is the inferior mesenteric, which I guess they didn't even label on this diagram. There it is right there. And it goes to the left side of the colon and the sigmoid colon and the upper parts of the rectum. So that's the 3 unpaired arteries. Notice, of course, that the renal arteries are paired. There's also some lumbar arteries that come off kind of at every level along in there. And then these are important right here. These guys, which are illustrated here and here, I'll bet on this picture they're called the gonadal arteries. Here they are right here, the gonadal artery and vein. Now the important point for you to remember is that the gonadal arteries, obviously in the male, they go to the testicle to supply blood to the testicle. In the female, the gonadal arteries are called the ovarian arteries because they go to the ovaries. Those are the female gonads. But notice that despite the fact that the ovaries live at about this level down here in the pelvis, and of course the testicles then live about down here off the page, they come off way up high. They come off just a little bit below the kidneys up here, like in both sexes. And the reason for that is that early in our development, when we're a little bitty fetus and our body hasn't even decided whether we're going to end up being a boy or a girl, the ovaries and the gonads form up there. And then as we mature a little bit and the decision is made due to some hormones, whether we're going to turn into a boy or whether we're going to turn into a girl, then they migrate on down. If they're testicles, they migrate all the way down into the scrotum. If they're ovaries, they migrate all the way down into the pelvis where they hang at the end of the oviducts by the uterus. So always be aware of that, and we will see these in our cat. You'll see the gonadal vessels. You should pay attention to them. Here's the ureters, the tubes. The ureter tubes are pretty small, and they're not very exciting to look at. And one of the problems that we had at surgery was seeing them and telling what they were, because you didn't want to cut one of them. That would be a bad move. But what you could do was, with a pair of tweezers, you could tweak it. And every time you tweaked it, it would peristalse. And so you tweak it, and then you watch a peristalsis go down the ureter. Tweak it again, and watch another peristalsis. And that was the way we would identify those little tubes as ureters. The fact is that the kidney is making urine all the time, and the ureters, therefore, are peristalsing sort of all the time to carry the urine down. The bladder starts out really small, it fills up really big, and when it gets full, then obviously it empties itself. The hilum of the kidney is the main entrance, the side entrance to the kidney, where both the renal artery, the renal nerves, the renal vein, and the ureter. So these two are going in. The renal artery is carrying blood into the kidney. Renal nerves are carrying some nerves into the kidney. The renal vein is carrying the blood out of the kidney, and the ureter, of course, is bringing the urine out of the kidney that the kidney made. This is a cross section of the kidney. We will give you kidneys that are have been injected, red for arteries, blue for veins, and then you can cut your kidney in half. And when you do cut your kidney in half, you should get a picture that looks a lot like this. The artery and vein are not illustrated on this picture here, but you'll see them on the back side. This is the ureter coming out. These things here are the collecting ducts that collect the urine. The urine is actually made in these things called renal pyramids here, and the urine comes out through little holes right here at the tips of each one of these little papillae. So this is the renal medulla in here. Medulla is like, for lots of organs, we have a medulla, and then we have a cortex. The cortex is the outer layer. The cortex, as you can see, is this whitish area from and the outside out here. Just for a heads up, the cortex is where we're going to find all of the glomeruli, little gloms of arteries and veins. That is where the process of creating urine really starts. They're out here in this. And then they eventually work their way through some tubules, and they go down here into the renal medulla. They go down, they go up, and then they come back down a third time and empty out through these little papillae right here at the end of those pyramids. When you get your kidneys and you're dissecting them, I want you to notice the fact that you see this little fat right in here, and right there, and right there. That's really not even in the kidney. That's what's called the renal sinus, because if you just kind of stick your finger in on the front side of the collecting system here, or on the back side, you'll see that this fat, which is filling into empty areas in there, really isn't in the kidney itself. It's really just kind of around it. These areas that connect down there are called the renal columns. And I think I'll just leave it at that for now. Here's what the living thing looks like. It's the same exact picture. It's just not quite as obvious as that last one was. The key to making urine is following the filtrate as it flows through the nephrons. And remember what we called the unit of bone? In compact bone, we called it a osteon. Yeah. Well, this is a nephron. And a nephron is the unit of kidney. Basically, it's the part of a kidney that makes urine. So these nephrons are microscopic. You can see them under the microscope very easily. And they are tubes, a bunch of little tubes that start out in the cortex on the outside of the kidney, and that's where urine production begins. So basically what I'm going to be talking about for the next day or more is how that fluid passes through these different tubes as it passes through the kidney, how certain things are added to it, how certain things are removed from it, until we get the final product, which we call urine. Okay? I'll just leave it there. Blood supply to the kidneys, lots of blood goes to the kidneys, 1,200 cc's a minute. 1,200 cc's a minute, think about that. Somebody got a liter bottle of water around here. That's probably about a liter right there. You can imagine if that thing was being filled up every single minute with blood, that's a lot of blood flowing to the kidney. And it gets it through the renal artery, as I mentioned before. Well, what about sympathetic innervation? Remember that rest and digest stuff and that fight or flight? Well, obviously, sympathetic innervation, the fight or flight mode is very important in the kidney, because if you're in fight or flight mode, are you going to worry about making urine? No, you're gonna squeeze down the renal arteries that go to the kidney, and you're gonna sort of slow the blood flow and therefore you're going to slow down your urine output. In fact, you're probably not going to make hardly any urine when you're in sympathetic output. The best example to help you remember that is if you ever run a marathon. They have a whole lot of porta potties at the beginning of a marathon. That's because everybody's nervous, and they might only have 20 cc's of urine in their bladder, but they feel like it's full and they got to go pee before they start. But once you start running, you probably don't make any urine the rest of the race because you're sending all of your blood to your muscles and to your lungs to breathe with and so forth. And so that's why the sympathetic innervation is very important. Sympathetic innervation also causes the stimulation of this hormone called renin. Renin means kidney, obviously. And what it does is it stops the losses of water and salt. So you got to remember that we can make 3 liters of urine in an hour. If we have a whole bunch, if we're sitting here drinking water one right after another, we can make 3 liters or more of urine in a single hour. But we can also, if we're exercising and we don't want to be making urine, we can make 5 cc's of urine an hour because we don't want to lose that fluid. We want to save that fluid to pump through our blood vessels and also to sweat with when we're exercising heavily. Okay. This is something you're going to need to know. It's the blood flow to the kidneys. It's really not all that hard, but it does have a few names to it. So here's the renal artery coming in, and about the only branch off the renal artery is this little suprarenal artery that goes up here and then goes to the adrenal gland, which lives on top of the kidney. The adrenal gland actually gets 2 other blood supplies, but this is one you'll probably see. So then it comes on up here and it starts breaking up into 2 or 3 segments. So this is called a segmental artery, as illustrated right there. And then those segmental arteries come on up here, and they form these interlobar arteries. So they go between the lobes. This is a lobe, this is a lobe, and the interlobar arteries come up to here. And when they get to this line right here, which is really the line between the medulla, the medullary part of the kidney, which is the middle parts, and the cortex, which is the part out there, they split and go both ways. And when they do that, they're now called the arcuate arteries. And here it is, right here, arcuate arteries that arc around both directions. Coming off of the arcuate arteries are these ones that go straight out, and we call those the cortical radiate. In other words, they follow the radius. They're up in the cortex, so they're cortical radiate arteries. And these are the arteries that are actually going to send blood to the glomeruli, which is the first part of the nephron, which is the first place where urine starts to be made. Okay? It comes back through veins. They're all named the same thing. They're called arcuate veins and renal cortical veins, and then interlobar veins, and then segmental veins, and then the renal vein. Okay, easy enough. Renal vein enters into the, what does it dump into? Inferior vena cava. Thank you. Thought I was going to have to kill myself. Okay, meanwhile, back here, here's a little more close-up. Here's the segmental interlobar arteries right here, becoming the arcuate arteries and arcing around like this. And then please notice that those cortical radiate arteries, which go out this way, just simply go out towards the surface of the kidney. But as they do, they form a whole bunch of these little, they look like grapes on this diagram here. Each one of those is a glomerulus. Now, when I say that word glomerulus, I usually call it a glom. It's like a glom of little arteries, and they just kind of buzz and go all around and run around in circles in this little glom of arteries called the glomerulus, and that's where the first filtration is going to happen and where the first urine is going to be formed. There's just those arteries that we've already gone over. Okay. Now, I have tried to teach this a number of times, and I've tried very hard to make it very clear. And I finally found out that one of the things was if I just started at the beginning and went through it with the students, they kind of saw the trees, but they didn't see the forest. So then I started putting in a slide or two up front here to let you know where we're going to. Okay? So this is a picture that summarizes renal function. Okay? And you'll see this in your book. It's in there plenty of times. But let me just go over this, and I'm going to take 2 minutes here to kind of jump ahead and let you know kind of what we're going after. The blood comes up, and the blood comes up through these arteries that we've just been talking about, and it goes into this thing here called a glomerulus. It's illustrated right here. So that glom is a whole bunch of arteries that just kind of ball around and run around with each other, and then they go in there and they leave. And they have a little control valve going in, and they have a little control valve going out. And think about it like this. If I had a pipe that was sending blood over here to the kidney, and I've got a pipe coming in, and I've got a pipe coming out, okay? And if I could open the valve really open on this side, send a lot of blood in to those glomeruli, and then on the other side over here, coming out, I could tighten it down really tight, so it's very hard for that blood to get out. A lot of blood would be pushed out of the arteries because these arteries have kind of open sides. They're kind of like screen doors on the side. And so if the pressure coming in is high and the pressure going out is low, we push a lot of the blood out of the arteries and into this thing here, which is called the renal capsule, or the renal well, it's the cortex, but it's the proximal tubule, the renal tubule. So it pushes this water out into here, and it doesn't push the proteins out because the proteins can't get out through the little holes in the side of the artery, but it pushes a lot of water and salt out here into the tubule. And from this point forward, it's going to be a long process to actually purify it till it's really urine. The fluid in the tubule will come this way, and it'll go down through this tubule, which is called the proximal, goes through what's called the proximal convoluted tubule. Then it'll go through the descending limb of the tubule. Then it makes a loop down here, which is called the loop of Henle. Then it comes back up. It goes through the ascending loop, comes up here, does another little loop through the distal convoluted tubule, and then it comes back down here and heads out the final time down, and this is now called a collecting tubule. When the urine, this fluid, which we've been calling filtrate, gets all the way down to here, we now call it urine. And from there, it just goes out. It goes out through the ureter and out to be peed out. In the process, we've done a lot of stuff. And you'll see here's water coming out. Here's sodium and chloride being pumped out. Here's H2O being pumped out here. Here's sodium, more sodium. Here's different things being secreted, sugars being put back in, proteins are being put back in if they got out, and so forth. So there's a lot of things that happen as it flows down these tubules and flows through these different parts of these tubules before it actually becomes urine. Okay? We got to start somewhere. And so we're going to start and go through this system starting at the glomerulus. Okay? The basic processes involved in making urine are three. The first one is called filtration. Filtration is pretty simple. Filtration is based on size only. So that it's kind of like, you guys ever make spaghetti and you've got a colander at your house and you take and the spaghetti's on the stove and it's been boiling, and then you take it and you dump it through the colander and all of the water just runs right out of it? right? And the spaghetti stays in the colander, right? Why does the spaghetti stay in the colander? Because it's big, okay? It's big, it can't fit through the holes. So think of the spaghetti as the proteins. So when our blood flows into that colander, so to speak, the only stuff that can get out is the water and the small things like salt, the chloride, and so forth. But the big things stay in the bloodstream, okay? So that's the first step. Everything starts with filtration, and you'll hear this word a lot. Then the next process involved in making urine is called reabsorption. And basically that means the body says, wait a minute, we don't want to lose all this water, let's reabsorb some of it. Oh, by the way, we don't want to lose all this salt, let's reabsorb some of it. We don't want to lose all this chlorine, let's pull those chloride ions back into the body, okay? So the second part of making urine is called reabsorption. And reabsorption is just what it says. It's bringing things out of the renal tubules, out of this stuff that's going to be urine eventually. It's pulling that back into the bloodstream, back into the body. Okay? Does that make sense? The third step is called secretion. Now, I think this is a confusing word here because it doesn't mean that we're going to secrete a bunch of urine or we're going to secrete a bunch of stuff. It means that it is secretion, but it's mostly things that we really want to get rid of that just didn't flow out. Either they were the wrong size to fit through the filtration thing, or we just want to get rid of them. And so we have processes in the kidney on downstream a little bit where secretion takes place. And this is where we actually pump things out back into the urine. We pump them because we want to get rid of them. If we want to get rid of them, we pump them into the urine, and then they're going to be out of our body, right? Okay. So we're going to talk about each of these in pretty much detail as we talk about how our kidney actually makes urine. Meanwhile, back to the nephron. The nephron is this long tube thing that goes up and down and all around that makes up the unit that makes urine. The renal corpuscle is the first part of it, and then the rest of it is the renal tubules. And I don't know why we put it in this order here on this slide, because strictly the renal corpuscle is where this all started. This is the glum of arteries, okay? So the renal corpuscle is a spherical structure. It's nice and round. When you look under the microscope, you will not have any trouble at all seeing the glomeruli. They're round. They look kind of like islets of Langerhans. They're so different from all the other tissues around them. And really what they are is just simply a bunch of blood vessels. So the glomerulus is these arteries. So you could draw it like this. You could say, okay, there's an artery coming in. And by the way, let's just call that the afferent artery. And that afferent artery comes in, and that artery winds around here in this glom of arteries, and then it goes out, and it goes out through another artery. And what should we call that other artery? Efferent artery, yeah, the efferent artery. So the exiting artery, efferent, is going out. The important point that you understand is that both of them are arteries. This is not an artery coming in and a vein coming out. They're both arteries. They're both under rather high pressure. And because of that, we can change the pressure here. There's muscles in the wall that change, that let more in or more out. And on the efferent artery, we have arteries that open up and let more out or let more in. And clearly, if you want to make the most urine, the way to make the most urine is to have your afferent arteries wide open and your efferent arteries closed down, because that's going to mean there's a lot of pressure in this thing, and that's going to push the water right out through the walls of these arteries in the glomerulus. Surrounding the glomerulus is this thing called the renal capsule, the renal corpuscle. So the glomerular capsule is this thing here that the urine, what's going to be urine, this fluid, this filtrate, gets pushed through into here. And from this point in, it's called filtrate as it goes on downstream and gets more completely purified into just what we want to get rid of and what we don't. We actually showed you renal glomeruli on the first day or second day of 231 because we showed you Bowman's capsule, which is what this capsule is called, and we had you look at these cells right here because these cells are simple squamous that line this capsule. You might figure they would be simple squamous because all they're going to do is act to allow fluids to flow through them to get out, to get into the capsule here. Okay? Got that, Elizabeth?
I do. You should probably upload your new version of your slide PowerPoint to D2L.
Why?
Because we don't have that one.
You don't have that slide?
No.
Gosh.
And like 5 other slides that you mentioned.
Sorry.
Just throw it out there.
I have no idea where the next copy is. I've got so many copies of all these lectures, it drives me crazy. All right. So anyway, here's the glomerulus talking about it. It's basically about 50 intertwining capillaries. Blood goes in through an afferent arteriole. Blood leaves through an efferent arteriole. And once it leaves the efferent arteriole, once it comes out up there at the top, it then enters into these peritubular capillaries. And the reason it does that is, well, I'm going to say that right now. Let's keep going. So the only place in your kidney where filtration occurs is here in the glomerulus, in the renal corpuscle. This is the only place that filtration happens. Blood comes in, pressure filters a bunch of stuff out, and that becomes the filtrate that then we're going to work on and perfect until it's perfectly crystal golden urine, right? And just to digress for a second, one time when I was a surgical resident, I was running a 10-mile race, and I had a heat stroke. It was in the spring in Washington, D.C., and my temperature was 108, and they took me to the emergency room, and I was in coma. They told my family to go home. They said, he's not going to make it. He's going to die. And I didn't know anything about it. 12 hours later, it was about midnight, and I woke up, and I found myself laying in the intensive care unit at George Washington University in downtown Washington, D.C., which happened to be the same ICU where Ronald Reagan was taken when he was shot. Anyway, so I'm laying there, and there's 2 nurses over at the desk. There's maybe 4 beds in the whole place. And I've got little curtains on either side of me, and I see these nurses sitting over there, and the lights are down except for a little light they have on their desk. And I said, hey, what's going on? Where am I? They said, hey, he woke up! And because they weren't expecting me to wake up. So anyway, I said, what's going on? They said, well, you had a heat stroke today, and your temperature was 108, and your liver functions and your kidney functions are all completely abnormal. And, it's a bad deal, but it's good that you're awake. That's a great thing. I said, well, call the doctors and tell them. I'm sure they'll be glad to be woken up at midnight. But as I lay there, I thought to myself, heat stroke. I was a second-year surgery resident. I thought I was pretty smart. And I think I'd read a few things about heat stroke, but I wasn't all that bright about it. But I did remember this, and that was that you needed to make urine. And if you weren't making urine, your kidneys were probably shutting down. And if your kidneys were going to shut down, you were probably going to die. because everything else was going to shut down too. So luckily, I had a CVP line in my subclavian on both sides. I had a bunch of temperature gauges up my nose and up my butt. I had a Foley catheter in my bladder. I had an arterial line and I could see my pulse rate up there on the wall from my A line. And I looked down there and I could see that I didn't have any urine in my Foley tube. And I thought, that is not a good sign. So I'm laying there and the nurses are over there minding their business, and I'm looking up and I see there's a big IV bag here and there's a big IV bag there, and I put my hands up there and I undid the little roller clamp on both sides and they just went, and I gave myself 2 liters of Ringer's lactate, IV fluid, salt water. And after I'd gotten in about 1.5 liters or so, I looked down, and sure enough, there was urine in my tube, and it was coming across my leg. And I saw that golden stuff, and I thought, I'm going to be okay. I'm making urine. I'm making pee. I've got kidney function. Because I'd had lots of patients in the ICU by that time, and I knew if they were making urine, they were going to be okay. That's usually was the case. And I'll never forget that. And so I sat there with those IVs running, and then it just started coming. And first it was dark, then it got lighter, and then it got clear. Then I reached up and turned the IVs down, and then, 30 minutes later, the nurses came on and said, "What happened here? Oh, that IV fluid wasn't supposed to run in so fast." I don't know. I had no idea. Write up an incident report, But the point being, it's just simply that if you give yourself enough fluid, if you have enough IV fluid and blood inside of you, and you've got enough pumping to your kidneys are going to make urine. And if your kidneys are making urine, that tells you, as I said a little while ago, you've got enough blood pressure, you've got enough blood, your heart's working okay, your lungs are working okay, pretty much everything's working okay if you've got urine output. So now after we've made this filtrate here, and the blood and the filtrate has started down this little tube here, it is now in the renal tubule. This is the renal tubule right here. And that renal tubule is going to then do a bunch of different things. There's going to be a part of it called the proximal convoluted tubule. There's going to be the descending loop of Henle, the ascending loop of Henle. There's going to be a distal convoluted tubule, and so forth. So, and all of these different parts of that renal tubule are going to be trying to do something else with that filtrate. They're either going to be trying to put stuff in to get rid of it, make it urine, or they're going to be trying to pull stuff out, okay? Pump stuff out of the renal tubules in order to save, to keep inside of you, okay? Does that make some sense? So what's going to happen is from the time the fluid leaves right here and starts down the renal tubule, we're going to reabsorb a lot of useful organic nutrients that were pushed out, like sugar. The sugar just got pushed out with the spaghetti, right, with the water from the spaghetti, and became part of the filtrate that's in that tubule. Then we're going to also reabsorb more than 90% of all that water. So even though we poured it out and it went through the colander and it came out of these arteries and it came into here, we're going to eventually reabsorb 90% of that. And if you think about that, that means that we formed 10 times more fluid into the renal, 10 times more fluid down here than we actually are going to pee out. Okay? We're going to reabsorb 90% of it as it goes down the way. Make sense? And then the final stage, the third one, is the secretion. We're going to secrete waste products that we didn't get rid of just by filtration. We're going to actively pump them into the urine to get rid of them as well. Okay. In the cortex, now, remember looking at our picture of the kidney from a few minutes ago. Here's the kidney. And here's the dividing line between the cortex out here and the medulla down here. Okay? Most all of these glomeruli are located out here in the cortex, like I showed you on that. Looks like Brussels sprouts, kind of, doesn't it? You know how Brussels sprouts grow, Miss Taylor? They grow on trees. They grow on bushes. How do Brussels sprouts grow? Anybody know this?
Tree.
We grow on central stalks.
Stalks.
Yeah. They grow on stalks. And the only reason I know this is because I was in Fred Meyer's about a month ago, and they were selling stalks of Brussels sprouts. And it's a stalk about this big around, and it's got little Brussels sprouts on all sides, and maybe they're in a piece this long. There's maybe 20 of the little sprouts. Why did he say that? It sounds so stupid, Sessions. I wanted to go back and show you that other picture. I guess I can't find it now, probably. Yeah, right here. This looks like a stalk of Brussels sprouts right here, doesn't it? With a bunch of little glomeruli on either side. Come on, help me out, guys. Help me out. Okay. Anyway. This is an important point right here, is that this filtration, remember, it was just a pressure thing, and the fluid that comes out of there does not have proteins in it. The reason it doesn't have proteins in it is because the proteins are very big, and they won't fit through the little holes in the walls of the arteries that let it out. They don't fit through the colander. Okay? So pretty much you could say that filtrate is like blood plasma. In other words, it doesn't have red cells in it, and it doesn't have any of those proteins in it, which means it also doesn't have any of the lipoproteins in it, the good cholesterol and the bad cholesterol and that stuff, so forth. So it's pretty much like plasma. All right, I've said that already. I'm going to skip collecting ducts. Let's talk about these guys here. We have two basic types of nephrons. One is called cortical nephrons, which are like these guys right here. And the difference between cortical nephrons and juxtamedullary nephrons is that the descending loop of Henle here, the descending thing, is much longer in these juxtamedullary nephrons. Now, what does that mean, juxtamedullary? Well, it means they're pretty close to the medulla. Okay, they're juxtamedullary. And so the glomerulus here is close to the line between cortex above, medulla below, but they go way down in here. And these are the ones we're mostly going to talk about as we go through this, because it's these long ones like this is what allows us to concentrate our urine and make really thick urine, which means we don't have to make a lot of urine, which means we can save water, which is really good if you live in a hot climate, or if you're a squirrel. All right, this is a bigger picture of what I drew over here, but here's the glomerulus right here. Here's the afferent and efferent arteries, the afferent coming in, the efferent coming out, a glom of blood vessels right in there, and here's the capsule going around it. So any fluid that gets pushed out through the walls of the aorta the walls of the artery become filtrate, and then they start down through these renal tubules. The first area is called the proximal convoluted tubule, first area. Then it enters into the descending limb of the loop of Henle. Descending loop goes way down here, and then it comes into the ascending limb, which goes way back up. And when he gets up to the top here, it enters into what this thing here is called the distal convoluted tubule. And these little boxes tell you kind of what happens in each of those. After it's gone down and back, it heads into the collecting tubules, the collecting duct rather. The collecting duct, all it does is reabsorb water. So we reabsorb the water, and then what's left down here, when it gets to this point, what's called the papillary duct, which is on the tip of those little papillae, is actually called urine. Okay, that's the first time that we call it urine. Up until that, we just called it filtrate. About 85% of our nephrons are what we call cortical nephrons, which means they're kind of up in the cortex. They have a very short loop of Henle. In other words, it's up here, it comes down a little bit and goes back up. It may not even get out of the cortex. It stays up high. And then the other ones, the 15%, which, like I said, are the ones we're going to study most about, are called juxtamedullary. So they live right down here on the dividing line between cortex and medulla. And even though they're close to the margin here, they go way down here. They're really long loops of Henle. In fact, we call them vasa recta, or the tubule, the capillaries that run along with them. Vasa meaning blood vessel, recta meaning straight, right? Rectum, straight. Rectus abdominis, straight. Okay. I think I'm going to stop right here. And because I have some videos that I want to show you that are real short that I think do a good job of explaining how things move in and out of the renal tubule as it passes through the different parts. I think you would be very well served if you could read a good bit of this chapter by the time we meet next time. Okay? Have a great weekend. Have a great Super Bowl. I'm going to Seattle for the weekend. Huh? Yeah. I like Seattle a lot. It's just rough. Yeah.
Maybe that's why
Well, have you seen how many developments are going on? Oh, it's unbelievable. I tell you, when I leave here, I go that way down Springville, and then I go down Kaiser or something, Free Spectrum, and then I go that way down. When you get to Cornell, I go that way, and then I usually take a left, a right, and go out on 26, just before I get into 217. It really is. But you know what? It was country. 2 years ago, you went down there, it was country. Now you look at it, I know there's more than 1,000 new housing units. Apartments, condos, houses that are 5 feet apart down there. And there's stores, and there's theaters, and there's everything. Yeah. It's like, oh, I know. It's to the point right now where you've almost got to live out in North Plains to get a reasonable price.
It's not to see people selling more and more land. You know, they go to development.
Huh? Oh, I know. That's what we were just saying. Worse in the whole country. But it seems to me like it's getting worse here. Okay, I'm going to try to record this, and we'll see. I saw a little note on Facebook. First of all, thank you, Gina, for responding. I thought those were pretty good ideas. And I saw a note from Melissa saying that y'all must all have this renal physiology down because not but one person showed up at open lab the other day, which usually means it's because we just had a test, and I understand that. That's okay. But one thing that she does is she does in open labs about this time, she does these drawings on the board that put all of the renal physiology on a big diagram on the whiteboard. And sometimes it'll stretch across four whiteboards like this. And I think it really helps with your understanding. If somebody would like to encourage her, I'll talk to her too if I see her. I'm not seeing her but about once a week these days. Encourage her to do that. Maybe somebody can videotape it, her going over the whole thing. And I think you'll find that very helpful because this does tend to be a little complicated and involves a lot of steps. Yes?
I could do that tomorrow night. Go to open lab and report.
That'd be lovely. Yeah. So anyway, we're going to kind of go through this urine formation today. We started on it a little bit yesterday. We talked a little bit about filtration. Filtration is the first step in creating urine. And filtration is very crude and it's very simple. It works on pressure. And it's just like squeezing fluid out through a semi-permeable membrane, and everything pretty much just flows out. It's kind of, I use the example of the colander and the spaghetti. The spaghetti noodles are like the proteins that don't pass through the wall. Everything else, all the water and stuff does pass right out. And now we're going to break that down and take it step by step. Did I start this? Okay, so this is filtration. This is the start, and this is the first phase of urine formation. And just remember that filtration is pretty crude. It's nothing more than filtering it. It's done mainly by pressure. In some sites in our body, we have really large pores in the walls of the endothelium, on the inner linings of the blood vessels. For example, in the liver, where the blood just kind of pours out amongst all those hepatocytes, and the other places in the bone marrow where blood just kind of pours in at one end and kind of pours out at the other. At the renal corpuscle, we do have a somewhat more specialized membrane. The renal membrane, the renal arterial membrane is good enough that it does not let out the proteins. It keeps all the proteins in. We should never pee out protein. We talked about that in the metabolism chapter. Proteins are hard to make. They take a lot of energy to build. We certainly don't want to just be peeing them out in our urine. Those of you who are pregnant have been to the doctor, and every time you go visit the doctor, they make you pee in a cup. And the reason they do that is for only two things: to check if you have protein and to check if you have sugar. A lot of ladies will become gestational diabetics during pregnancy, but then that reverses at the end of pregnancy. Wow, how long did it take you to do that?
Oh, 7 hours.
7 hours.
Yeah.
My
Did you do it
goodness,
yourself or
that's
did you have
impressive.
it done?
Huh?
Did somebody help you?
Yeah.
Okay, thank you.
Somebody else did it.
Oh, well,
Yeah.
She paid someone to do that.
Yeah.
you studied. Like,
Studying law.
That is impressive. I like it.
Thank you.
Well, meanwhile, back to renal physiology. I forget what I was saying. Could have been very important. So anyway, the blood pours into the kidney, and it goes through all those little blood vessels that we talked to, and then it gets to the what's called the afferent arteriole, which is the artery that's carrying blood into the glomerulus. The glomerulus is that little glom, that little collection of arteries. And so the blood goes in. You'd like to think it goes in pretty easily, but it has a hard time getting out. So sure enough, the efferent arteriole, the exiting arteriole, requires a pretty heavy pressure to get out through, and that encourages us to force blood out of the arteries, out through the slits in the walls of the arteries, out into the glomerulus. So, what we're going to talk about now is the pressures necessary to generate filtrate. Filtrate is the name of the fluid that comes out of the arterioles and forms the first phase of urine. So if this is the glomerulus here, this is an artery, right, illustrated right here. This is blood in it. These are the slits in the walls of it, as you can see around through there. And this is blood in here. So blood has lots of proteins in it, as illustrated by these blue blobby things. Remember the pressure going in, it was easy to get the blood in, but the efferent going out is high pressure, and so therefore it tends to force a lot of fluid out of the glomerulus, out here into this thing, which is called the capsule, the renal capsule. And then it starts, once it collects out in here, it heads down the renal tubule. And this renal tubule has got about 6 parts to it. We'll go through them part by part and try to explain what's happening. But to make urine, you've got to make filtrate, okay? And normally you have to make a lot of filtrate. In fact, we reabsorb, farther on downstream here, we're going to reabsorb 99% of this filtrate that we made here in our glomerulus. So what are the pressures that make the fluid come out? And I already mentioned the biggest one probably is the glomerular hydrostatic pressure, which is basically the difference between the pressure going in and the pressure going out. So that's a difference of about 50 millimeters of mercury. So we've got 50 millimeters of mercury pressure pushing fluid out of the arteries, out into the capsule here, and becoming filtrate. Now, what pressures oppose that? Well, one of them is the blood colloid osmotic pressure. That's sucking water back in, because remember, this is going to be much more hyperosmolar than this is out here, because this has all the proteins in it. So this has a whole lot more stuff that's osmotically active. It's stuff in solution, right? And so there's going to be a tendency by plain old osmosis for fluid to go back in there. Now, just to refresh your memory on osmosis very quickly, not to beat too many dead horses here, but if we went back to our basic 112 and we were thinking about how osmosis really works, let's create us a beaker. And let's put a semi-permeable membrane down the middle of it. And let's put 15% glucose solution on this side. And let's put pure water on this side. Okay? Which way is the water going to move by osmosis? It's going to move this way. That's right, because water is more concentrated on this side. It's 100% concentrated, and there's all this glucose in here, so the water is less concentrated on this side. So water is going to go this way. And as it does, it works its way that way until it reaches equilibrium. And let's just say it reaches equilibrium at this level right here. Okay? So we have 2 pressures that are working on us right here. We have osmotic pressure, which is pushing this way, right? And we have hydrostatic pressure, pressure, right? The height of the water tower or whatever, that's pushing down this way. So when this pressure down equals that pressure that way, it's going to quit moving. It's going to reach equilibrium at that point. okay? I think it's always kind of hard to really see osmotic pressure, but that's it right there. Here you have osmotic pressure pushing this way, you have hydrostatic pressure or gravity pressure pushing this way, and they come equal, okay? The same thing is going on in your kidney, like this. Let me just advance something here. Yeah. So we have 50 millimeters of pressure, hydrostatic pressure, just we're squeezing it, it's going out. That's hydrostatic pressure pushing the fluid out. And then we have opposing that, we have 25 millimeters of blood colloid osmotic pressure. Because remember, blood is a colloid, it's got all that protein in it. So we've got pressure working its way back this way. And then we have this other pressure down here called capsular hydrostatic pressure. What does that mean? Why would there be hydrostatic pressure going that direction? Well, it's simply because this thing is making so much fluid, so much filtrate is dumping out into here that it can't run off fast enough. And because it can't run off down this tubule fast enough, it creates sort of a back pressure. And that's what this last 15 millimeters back pressure is. Okay? So it is capsular hydrostatic pressure. You put them all together, put those three pressures together, and you get a net filtration pressure, which is the big blue arrow, of about 10 millimeters of mercury. Okay? Now 10 millimeters of mercury may not seem like a lot, but it really is. And indeed, we are creating a total of about 125 cc's of filtrate every minute in our bodies. So we're making 125 cc's a minute of filtrate. Now, that means that if all of that fluid eventually turned into urine and came out, we would have to go to the bathroom every 3 minutes. Because that would be 375 cc's every 3 minutes. That would be a pretty significant urination. The most we can usually urinate is about 700 if we really fill up really full and it hurts so bad. Okay? So we're making tons of filtrate all the time. And that's the important point because this is the first step in making urine. And if we don't make filtrate, we don't make urine. Okay? Just quickly go over these pressures again so that I think you really understand them. The colloid osmotic pressure of a solution is the osmotic pressure resulting from the presence of all those suspended proteins. And indeed, the blood colloid osmotic pressure, BCOP, is the pressure that tends to draw water out of the filtrate and back into the blood vessels or into the plasma. Okay? So therefore, it opposes filtration. And as I said a minute ago, it's about 25 millimeters. The filtration pressure is just the pressure forcing it out. Leave it be. Capsular hydrostatic pressure is that pressure that's pushing back in. It's a hydrostatic pressure pushing back in simply because there's a resistance to flow along the nephron. The fluid just can't go down the nephron fast enough to not create some back pressure. And it averages about 15 millimeters of mercury, giving us this net hydrostatic pressure, putting them all together, of about 10. And that's it right there. Okay, so we've got these little balls of arteries here called glomeruli. They have an afferent artery that's wide open, usually going into them, sending lots of blood into the glomerulus, as illustrated up here at the top. The efferent artery coming out usually has a little muscle around there that clamps down a little bit so the blood can't get out as easily, and that tends to force more fluid out into the capsular space. GFR is normally about 125 milliliters a minute, and that is about 10% of the fluid that was delivered to the kidneys. Now let's see, if we're putting 125 milliliters, and that's only 10%, that means that we're delivering about 1,250 milliliters of blood to the kidneys every minute. Over a liter and a quarter of blood is being pumped to our kidneys every minute. That is a lot. That's about 25% of our entire cardiac output is going to our kidneys in order to make this filtrate so that we can filter our blood and clean up our system, get rid of our wastes. Well, we have a test that's available to help us estimate the GFR, the glomerular filtration rate. That number of 125 milliliters per minute is called the glomerular filtration rate. We have two tests that we can do in order to calculate how much GFR we're actually creating. The most commonly used one by far is called the creatinine clearance test. And the creatinine clearance test is really easy because we have creatinine that our muscles are making as a waste product all the time, and it's being filtered out. Very little of it is being reabsorbed, so basically what gets filtered out tells us how much GFR we made. We have a better test that's maybe a 10% more accurate test called the inulin test, which is just a dye that you give the patient IV. It circulates around, you collect their urine as it comes out, and by calculating all those levels, you can figure out what their GFR is. A little bit more accurate, but clinically not very, very necessary most of the time. A creatinine clearance is an easy number. You can calculate it very easily. What?
Isn't the creatinine clearance a 24-hour test, though?
Yes, it is.
Okay, yeah. That's okay.
You've got to collect a 24-hour urine to do it.
And you have to keep it refrigerated.
Yes, you keep it refrigerated. That's right. Pee in the refrigerator. So, I said we made 125 cc's a minute. Well, that works out to be 180 liters, 180 quarts of filtrate is made a day. Well, you can imagine how much that is. That's tons and tons and tons. But luckily, we're now going to reabsorb 99% of it as it goes on down through the renal tubules. Because remember what we said normal urine output was for a day? About 750 a day, yeah, or a milliliter per kilogram per hour. Okay. So, GFR is probably the most important number in studying patients' kidney function. Because it's, first of all, it's so important. If you don't make the filtrate up front, you're kind of stuck with kidney function. And basically anything that alters filtration pressure is going to alter the GFR. So think about that. Now, what could alter the filtration pressure? Blood pressure, okay? So if we altered blood pressure, that would be altering the afferent pressure, right? What else?
Oh, so is that...
Yeah?
So is that why if you're pregnant and you have high blood pressure, they automatically do a creatinine clearance?
Yeah. They want to know that your kidneys are actually working okay. Yes. So what else could alter the GFR, the glomerular filtration rate, the amount of filtrate you're making? Excuse me? Vasopressin? Yeah, what's vasopressin? ADH. Okay, that's right. You remember ADH from endocrinology? Okay. And ADH is going to determine whether or not we can reabsorb the fluid the way we're supposed to. Just let it go out if we don't have it. All right, what else?
Fluid intake.
Fluid intake. Well, that would alter the volume and therefore the pressure going. So yes.
Dehydration.
Dehydration would be just the opposite.
Solute concentration.
Solute concentrations. That's right. If the solute concentration was really high, we'd probably push more out, wouldn't we? Trying to get rid of it. All right. So what are the things that actually control the GFR? You guys came up with a pretty good list, and let's think about it. First of all, autoregulation. In other words, if more blood flows to the kidney, it's going to make more filtrate. That's just automatic, right? We don't have to think much about that. Hormonal regulation. You mentioned vasopressin. There's another one we're going to be learning about. It's called renin. You guys have heard of renin for blood pressure control. And so we do have some hormones that affect things down here. Another one is called erythropoietin. Remember, erythropoietin increases our blood volume, increases the number of blood cells, increases our hematocrit so that we can ride our bicycle farther, right? The only reason to take that stuff. And then autonomic regulation by sympathetic division. Think about this. The tiger just walked in the room.
I don't have time to pee.
You don't have time to pee. Well, it's not a matter of peeing that's the issue. It's a matter of, do you want to be making pee?
Yeah.
Do you want your kidney to be manufacturing pee when there's a tiger in the room? And the answer is no. You want to hang on to all your fluids. You want to hang on to all your salt. You want to do everything you can so you've got as much blood as possible to bleed if he bites you. You want as much blood as possible to have a higher blood pressure so that you can run farther and jump higher and kill the tiger if you have to end up fighting him, right? So all of that is why when the sympathetic system is stimulated, we don't make much GFR. So how can we do that? Well, there's some little slides here that are kind of nice, but really if you just think about them, they make sense. If you can dilate the afferent arteriole, what's that going to do? You're going to make more, right? If you dilate all of the glomerular capillaries, you're going to make more. If you constrict the efferent arteriole, the artery going out, are you going to make more or less? You're going to, you restrict the one coming out. You got more, you got as much coming in or the same coming in, but you've got to clamp down on the side going out. You're going to make more GFR, right? You're going to filter more out, push more out of the arteries, right? Rise in blood pressure or rise in blood flow, same thing. I just mentioned these. Basically, that's going to stretch the walls of the afferent arterioles. It's going to cause the smooth muscles to contract and fight you a little bit. And then that's going to eventually decrease your glomerular flow in order to compensate for this if you raise your blood pressure too much. Renin-angiotensin system, we've talked about it a little bit in the past. Now's a good time to really learn it well. And that's by hormones of the renin-angiotensin system. We'll go through that here in a few minutes, I do believe. 3 stimuli cause the juxtaglomerular complex to release renin. Okay, what is the juxtaglomerular complex? Well, the juxtaglomerular complex is this complex that's just up real close to the glomerular apparatus. So, indeed, we have an afferent artery going in. And then we have an efferent artery coming out, right? And in this area right here, we have a tubule, actually a distal tubule that has kind of curled around through the kidney and then come back through this area. And there's some sensors in this area that are going to sense just how concentrated that is. And this juxtaglomerular apparatus is then going to control the contraction of the afferent and the efferent in order to help control kidney urine formation. So, if you drop your blood pressure at the glomerulus due to a decrease in blood volume, that's going to cause the complex to release renin. Now remember, when you release renin out into your bloodstream, it makes you hold on to salt, and it makes you hold on to water. Okay, that's probably something you ought to remember. That's just one of the basic concepts here. So, if you have a fall in blood pressure, you're clearly not going to be wanting to make more urine. You're going to be wanting to hold on to everything to raise your blood pressure back up. So, a decline in blood pressure will cause you to increase your blood volume a fall in systemic blood pressure due to blockage in the renal arteries. Now see, the question is, how would your kidney know what was causing the decrease in blood flow? It wouldn't know if it's got a decrease in pressure because your heart's not working right, or whether you've got a renal artery stenosis. Think about what a renal artery stenosis is. Here's your renal artery. Here's your aorta. Here's your renal artery. And what certain people get is they get a buildup of cholesterol, just like they do in their coronary arteries. They can get it in their renal arteries down here. And obviously this renal artery is eventually going to connect to that afferent artery. And if this is narrowed, then the pressure here is going to be narrowed, and it's going to interpret that as we don't have enough blood, right? So if you don't have enough blood, what you're going to try to do is hold on to everything. So if that's going to fire off the renin's going to be released. Last thing is the stimulation of the juxtaglomerular cells by the sympathetic innervation due to decline in osmotic concentration of the tubular fluid at the macula densa. I feel like I should have talked about the macula densa by now, but the macula densa is this area right in here where the concentration of the fluid in the distal tubule is red, interpreted. What else is going to happen? Well, in addition to reabsorbing all the salt you can and reabsorbing all the water you can, it's going to start secreting aldo. Remember aldosterone, secreted by the adrenal gland, which also causes you to reabsorb water and salt. Makes you thirsty, so you suddenly have to go find something to drink. And it triggers the release of ADH, antidiuretic hormone, which Tristan mentioned, also called vasopressin ADH, which stimulates the reabsorption in the distal tubule and the collecting system as well. We'll get more to that. Okay, so another thing that the renin-angiotensin system does is that it causes your sympathetic tone to increase, which causes constriction of your arteries, causes powerful vasoconstriction. And it basically raises your blood pressure throughout your body. That's not a good thing in general, especially if it's going on all the time. This is one of the major causes of hypertension, high blood pressure, is overstimulation of the renin-angiotensin system. And indeed, a number of the blood pressure pills that we use today are designed to block renin and to block angiotensin, to lower folks' blood pressure. Aldo, you remember from the adrenal gland. I'm not going to say much more about it here. This is just kind of the natural body's response to a reduction in GFR. We want our GFR to stay nice and high. We want to be creating lots of filtrate all the time because that's the starting point from which we can make urine, and that's a good thing. So if we have homeostasis disturbed up here and that causes a decrease in our GFR, we want to make more GFR, so we cause renin to be released. Renin, when it's released, it causes angiotensin to be activated. That raises our blood pressure, raises our blood volume. Gradually, if we can raise our blood pressure and raise our blood volume enough, that's going to increase our GFR back. We're going to make more GFR and bring us back to homeostasis. An increase in our blood volume automatically increases our GFR. If we have too much blood in us, if we have too much volume in us, what are we going to do? We're going to make more pee. We're going to get rid of it, right? And that's just automatic. If we have an increased blood volume, we're going to have some other hormonal factors. What might be one of those? Well, I'll just tell you, we might make less EPO, less erythropoietin to accelerate not making blood as well. There's not much parasympathetic regulation on all of this, and so you need to be aware of but the sympathetic system is really what's controlling this. Yes?
What would cause you to have more blood?
A release of blood out of your veins, going from a standing to a down position,
Oh, okay.
things like that. I got it, I'm watching it. All right. So, in summary, let me just say that what we talked about to this point is filtration. And filtration is the first step in urine formation. And it only occurs one place, and that's in the glomeruli. Got it? There's two kinds of glomeruli. Remember, there's cortical glomeruli and there's juxtamedullary glomeruli. We'll come back to them. But basically, filtration is a very important step, and it occurs in the glomerulus. Now, let's talk about the loop of Henle. After the filtrate, and we don't call it urine yet, remember, after the filtrate is created and it comes out into the capsule here, I'll draw in the capsule. This is the capsule. And we actually showed you these on the first day of 231, or on the first day of the tissues lab, when we were showing you some examples of simple squamous epithelium. And we said, here, look at these kidney slides, and this layer right here is simple squamous epithelium. Remember that? No, you don't. Don't lie to me. Some of you do, I'm sure. I'm just kidding. Okay, so yeah, that's simple squamous epithelium. Once it gets out here, I'm going to move this from there up to here and say that now this connects to that. And then it goes through what we call the proximal convoluted tubule. In other words, it's just a tubule that runs through the kidney, and it's convoluted. So it takes a few bends around. And then it goes down through the descending and then back up through the ascending loop of Henle. And then it goes behind the screen and you can't see it ever again.
I think I was a big picture. Next question.
What?
So the nephron loop and the loop of Henle is the same thing?
Same thing. That's right. The nephron loop is the more official name these days. Okay, so we're going to talk about them a little bit now. The nephron loop, there you go, also called the loop of Henle. It turns down towards the renal medulla. So the renal medulla is down at the bottom of the table, the bottom of the board, and the outside surface of the kidney and the cortex are up at the top. Because remember, all of the glomeruli are in the cortex. Some of them are close to the line, and they're called juxtamedullary, but the rest of them are all out in the cortex. So it does this thing here. It turns down the descending loop. The fluid pours down here towards the renal cortex, and it has a thin segment and a thin segment, a thick segment and a thin segment rather, of the wall, and the filtrate continually comes down and then continually goes up. Now, I try hard to teach these concepts, which I think are sometimes hard to understand, but when I say that each limb, that means the descending limb has a thick segment and a thin segment, and the ascending limb has a thick segment and a thin segment. What does that really mean? Well, let me just try to explain it to you in really simple terms that I'm able to understand. The thin segments are kind of like a screen door. In other words, it's like a piece of screen. Things can flow in and out through it. Okay? The thick segments the cells that line that are thicker. And in my mind, I think, well, the reason they're thicker is because they have all these pumps in them. These pumps that pump things in or pump things out. Okay? So when you think thin segments, think things can flow through it pretty easily. And when you think thick segments, think, oh, there must be a lot of active transport going on here. There's a lot of pumping going on to pump things either into the urine, which we want to get rid of, or to pump things out of the urine back into our bodies that we want to keep.
So the thick segment would be like on the filtrate to reabsorb it.
Maybe. Different things.
Okay, and then
Just ride with me here.
the thin segment's going to be passive. It's the thin segment.
More passive, yes. So the first segment going down is the thick descending loop. It has functions that are pretty similar to the proximal convoluted tubule, and it is constantly, remember it's thick, so it's constantly pumping. And what is it pumping? It's pumping sodium and chloride out of the tubular fluid. So it's pumping salt and chloride. I'm going to draw it thick. I'm going to make the walls look a little thick here. Okay, coming down part of the way like that, and I'm going to say that it is pumping sodium and chloride out of the tubular fluid. So here's sodium, and here's chloride. Okay. Now, as we get a little later, we're going to be talking about the juxtamedullary nephrons and how they really concentrate our urine, make our urine really thick. Does anybody know how much you can concentrate your urine? How thick can you get it? In other words, the question is almost, how thick can you make your urine so that you can make as little urine as possible but still get rid of all your wastes? That's the way to think about it, kind of. We can concentrate it pretty good. We'll learn that in lab as well as here. The thin segments are relatively freely permeable to water. Remember, I said they were like screen doors. But they're not as permeable as you might think to solutes, especially things like proteins, if there are any proteins in there, which there really shouldn't be, but like glucose. Okay. As the water moves, it helps concentrate this tubular fluid. So if you have a certain concentration of stuff in here, and you'll see a lot of diagrams in your books, and they'll use dots to represent how much stuff is suspended in the fluid. If you take an area like that and you pull out all the water, okay, so we've got the water flowing out of the tubule going down here, then this causes concentration of the tubular fluid. So now the tubular fluid becomes much more concentrated. Why? Because the water's gone, right? So as you go on down the tubule here, that fluid is getting more and more and more concentrated. The thick ascending loop comes on up. This is thin here again, and then it gets thick again up here, and then it takes another turn. And I'm going to draw it this way because the fact of the matter is this is actually found right here. You just have to push it together on the board. So it comes back very close to the renal capsule, which it says here. And that's where the distal convoluted tubule begins. So then it does a bunch more little twists and turns as it goes on down. After the loop of Henle, we get to the distal convoluted tubule, which starts right here. And we can draw it kind of like this. I'll have you really confused with my lousy drawing. But anyway, This distal convoluted tubule is where a lot of really good things happen. The epithelial, it's the third segment of the tubule. It passes between the afferent and efferent arterioles. Remember this right here? Here's the afferent, here's the efferent. It passes right through them, right between them, right there. And it's getting smaller. It's smaller than the proximal convoluted tubule was. And off we go. Three processes take place in the distal convoluted tubule. The active secretion of ions, acids, drugs, and toxins. What does that mean? Secretion. Well, that means that our body is saying, we don't want this stuff. We want to get rid of this stuff, and we're going to pump it out of our body. To pump it out of our body, where do we pump it? We pump it into the filtrate, because it's headed out through the bladder. It's going to be urine, right? It's going out of us. So we actively start secreting things. And sometimes if we have too much potassium or we have too much calcium, this is where we start actively pumping it out to get rid of it. This is where we pump out additional hydrochloric acid. If our body is too acidy and our pH is too low, this is the place where the kidney gets rid of that extra acid. Remember I told you before that we have two major systems that control our pH. One is our breathing, right? Remember we're blowing out CO2, which is basically carbonic acid. And so we're getting rid of acid that way. And the other way we get rid of acid is through the kidney, right here, by secreting acid into the urine, which makes us pee more acidy. And you've probably been told, somebody in this room I'm sure has been told, when you had a kidney infection or a bladder infection at some time in your life, drink lots of orange juice or cranberry juice to make your urine acid in order to destroy the bacteria that are in your bladder. So by making yourself have an acid urine, which we do, that can help us fight off a little infection in our bladder without much trouble, without using antibiotics. Drugs. The book lists several drugs that are actively secreted. We get rid of a number of pharmaceutical drugs, prescription drugs, and so forth. We get rid of them through our kidneys. This is the part of the process. They're secreted here in the distal convoluted tubule. I think the book lists penicillin and a series of antibiotics that are all secreted in the distal convoluted tubule. And toxins, some bad stuff which we want to get rid of. This is where we do it. Along the way, we selectively reabsorb sodium and calcium from the tubular fluid, kind of like I was drawing over here. And the more we reabsorb water, the more we concentrate the tubular fluid. Well, let's talk a little bit more about this juxtaglomerular complex. This is the juxtaglomerular complex right there. It is a system that consists of the afferent artery going in, the efferent artery coming out, and between those, in the crotch of those two, we will usually find a distal convoluted tubule, a tubule there. And it doesn't look any different than the rest of the tubules. Maybe it's a little darker. They call it the macula densa part of it, and these juxtaglomerular cells, which are basically interpreting the concentration of the fluid inside of that DCT and deciding how can we fix this? Do we need to dilate the afferent arteriole to make more filtrate? Do we need to constrict the efferent arteriole to make more filtrate? Back and forth. It's kind of a fixing up place. So here's kind of what it looks like. Here's your glomerulus right here. Here's the afferent arteriole going in. Here's the efferent arteriole going out. Here's the distal convoluted tubule running past here. And notice this area right in here. These are these juxtaglomerular cells. And what the juxtaglomerular cells actually do is they actually read the concentration, macula densa right here. These are cells along this one side
of this distal convoluted tubule that read the concentration of the ions in the distal convoluted tubule here to decide how best to control the afferent and the efferent arteriole coming in and out. Now, on my diagram on the board, you see my proximal convoluted tubule came out over here and then wandered through the proximal convoluted tubule, then down and back, and then back around. But see, it kind of wanders around and gets back over here. Don't let the malposition of these confuse you. So much for the macula densa. I think I've said enough. Just remember that the juxtaglomerular cells are smooth muscle fibers that are in the wall of the afferent arteriole, and together with the macula densa, these juxtaglomerular cells form the juxtaglomerular complex, or the JGC. Yippee. But all of this is designed to help us read the osmotic concentration of the fluid inside that distal convoluted tubule so that we can respond to it and fix it. The goal of urine output, remember, is to maintain homeostasis by regulating the volume and composition of blood and also get rid of some waste products. There are 3 really important waste products that we have to get rid of, and we've talked about a couple of these already, but you need to know something about these 3. The first one is urea. Now, where does urea come from? We talked about it last chapter when we talked about deaminating things and tearing down amino acids.
Ammonia?
Right.
How we get rid of ammonia?
It's how we get rid of ammonia. So whenever we break down proteins, we create ammonia, which is toxic to us, and we send it to the liver, we run it through the urea cycle, and it comes out as urea. Well, urea is not toxic, and it's also easily soluble. It's very soluble in water, so we can pee it out. But that's important that we do. We have to pee out our urea. Now, any of those of you who have worked in a hospital setting have probably seen on the electrolyte levels a BUN, a blood, urea, nitrogen. So that's what we're talking about is BUN. That's blood, urea, nitrogen. But then we also check for UUN, urine, urea, nitrogen, collecting a 24-hour sample in the refrigerator and checking it. So urea is one of those things we want to talk about a little bit here in the kidney, and it's one thing we definitely want to get rid of. Creatinine is a breakdown product of muscle. We pretty much break down some muscle every day, all day long. We're always building new muscle as well, and creatinine is another thing that we measure frequently, especially if we're interested in kidney function. If we can't get rid of our creatinine, then our creatinine level builds up, and that's not good. That's a sign that our kidneys are failing, among other things. Creatinine level going up. Third one is uric acid. Uric acid is a waste product we need to get rid of. When uric acid builds up in our system too much, we get a disease called gout. Very good. Gout presents oftentimes as an arthritis, usually hugely swollen, red, ugly, painful big toe, which is the joints inside your big toe for some reason fill up with uric acid crystals, and you can see them under the microscope easily. You just have to put a needle into the joint, draw out half a cc of fluid, look at it under the microscope. You'll see the uric acid crystals, and you put the patient on medicine that will help them break down their uric acid. It's really very curable these days because we have wonderful medicines that will just simply take care of the uric acid and let it pass on out in our urine. Allopurinol is one of those drugs. So all of these products, those 3 organic waste products we just talked about, they're all dissolved in our bloodstream. They're only eliminated. The only way we can get rid of them is to pass them out in our urine. And in order to pass them out in our urine, we have to lose some water. Okay? We have to make a certain amount of water every day in order to get rid of our urea, our uric acid, and our creatinine. If we are not making much urine every day, those things are going to go up and we're going to be in renal failure before we know it. Whereas the normal BUN is about less than 20. Patient in kidney failure will have a BUN of about 180 often. And then every time they go through dialysis, it'll drop down to about 40, and then it'll creep right back up 2 days later, and they'll have to be dialyzed again. Creatinine will go up to about 9. It's normally less than 1, and then when they get dialyzed, it'll come down to 2 and go back up. Uric acid, I don't even remember what the numbers are, but it works the same way. Yeah?
Do you want us to know these values? Or
No. None of the numbers you need to worry about.
Because last test, there were some numbers I didn't think we needed to know. And I get those answers right.
Let's discuss them. We're going over the test here in an hour. I don't remember that. So anyway, now, how do we make a concentrated urine? That's the thing that I'm going to spend the last few minutes here talking about today. And I think this is maybe the hardest thing to understand about our kidneys. How do we take what's our normal osmotic concentration of our blood? Normal osmolarity of blood is 300. Very good. But yet, we have to be able to make urine that's 1,200 to 1,400 milliosmoles per liter. In other words, 4 times as concentrated as our plasma. So we don't have to run around peeing all day long, and so we don't have to run around drinking all day long like fish do. Okay? So how do we do that? Well, you might think, oh, that's no problem. We just have these pumps. So like, let's say this is our descending loop, and we just have some pumps in the wall in the thick part of it, right? And we just tell them, okay, just pump out enough water so that it goes from 300 in here, which it was when it was filtrate up here coming out of glomerulus. Just pump enough out so that it's down to, so it's up to 1,200 or 1,400, as illustrated there. And that would seem simple. The problem is that the pumps are not powerful enough. We can't pump that much difference in concentration. Okay? Now, why? So, that's, here we go. Let me go on here a little bit. I'll come right back to that. There are a couple of things that you do need to know. You'll need to know for this chapter and the next chapter. I will tell you there's a few normal values that you just need to know for us to be able to talk. Normal sodium level in plasma is about 140. Normal potassium level is about 4.5. Normal chloride level is about 100, and normal bicarb level is about 24. So, just so you know, we used to have a blood test which was called an SMA-6, and we ordered it on every patient every day if they had an IV or an NG tube or they weren't eating or drinking. And it had 6 tests on it, and those 6 tests were those 4 I just mentioned, which was sodium, 140, potassium, 4.5, chloride, 100, and bicarb, 24. 2 others were the BUN and the glucose. BUN normally less than 20, let's just say normal's 10, and glucose is normally less than 100. Basically, a lot of folks are diabetic, and especially if you're pouring sugar straight into their veins, a lot of people end up with high blood sugars. But those are the 6 numbers that we basically had to report to the attendings every morning on rounds. So pretty much most every patient that had an NG tube, that had IVs running, was going to get an SMA6 every day. And those are the 6 numbers that you needed in order to really know everything about their fluids and electrolytes. Remember that sodium is big on the outside of cells. Remember that? It's high in the interstitial fluid, which is what plasma is, which is what we test when we do blood tests, right? Remember potassium, which is really high inside the cells. It's like 100, but yet on the outside of the cells, because it's always being pumped in, it's really low on the outside. Potassium. Chloride's about 100. Bicarb, 24. If you're acidotic, that number goes down. If you're alkalotic, that number goes up. Okay, but our bodies are pretty good about controlling our pH, so that stays pretty close there. Then the BUN, blood urea nitrogen, is a number that's going to give you information about their kidney function, how they're doing, and glucose is going to tell you about their sugar. Okay, so I'm not asking you to learn any of these numbers down here. Urea, is about 10, which I told you up here. Creatinine is about 1. Ammonia, you should never really have any ammonia in your system unless you're in bad liver failure. There's the number for uric acid, which I didn't know, about 3. I don't know. I don't remember that. All right. Now this is just a list. You should have already known that. You should already know what these things are. You should know what facilitated diffusion is, what active transport is, what co-transport is, and what counter-transport is. I'm just going to leave them at that. As you read through this chapter in the book, it will point them out from time to time. But I don't really demand that you know these things in great detail. Just know what they are. These are different ways that we transport things through cells, right? I don't want to read that. Let's talk about renal threshold, transport thresholds, and let's go to the next slide, I think. What is the renal threshold of something? Well, the renal threshold is the plasma concentration at which we can't pump it all back into our bodies, okay? And it varies with the substance involved. And the one that you need to know about, first of all, is glucose. And normal blood glucose is below 100, but so at 100, you won't have any urine, you won't have any glucose in your urine, okay? But if your blood sugar gets really high, and if it gets above 180, your body can't pump all of that back into your body, so some of it spills out in your urine, okay? Anybody know a diabetic? Anybody know a diabetic that checks their urine? Not anymore, but I can tell you, 20 years ago, if you had diabetes, we didn't have these fancy little machines that you put 1 drop of blood on and it tells you instantly what your blood sugar is. The only thing we had was these dipsticks that you dipped in your urine 4 or 5 times a day, and it told you whether you were spilling sugar. 1+, 2+, 3+, or 4+ sugar in your urine. So all it meant was if you had sugar flowing out in your urine, you knew your blood glucose was at least 180. Because most people's kidneys, their renal threshold for glucose is about 180. They can pump 180 back into them. But when your blood sugar gets higher than that, then they can't. And some goes on out in your urine. My granddad used to have to do that 4 times a day. It was very crude. It always ran 4 to 6 hours behind what was reality. You know, when you check your blood sugar now, your blood sugar right now is 140, and you get the number right now. Back then, you found out what his blood sugar was 4 hours ago when he made that urine that then collected down in his bladder before it came out. You see what I mean?
So that could cause a lot of complications.
It was really tough. I mean, diabetics had to be incredibly intelligent. They had to be really well trained to accomplish anything to make it better. Yeah. And then they would read that, and then decide how much insulin to give themselves. And of course, a lot of folks back in those days, because the needles were so big, and the needles were so blunt, because they used them over and over and over again, it hurt a lot. Anyway, when glucose appears in your urine, we call that glycosuria. There's a word you ought to know. And that means that the threshold, the maximum threshold, has been exceeded, and sugar is spilling out in your urine. Now that also happens with amino acids. I told you we don't normally spill any proteins out in our urine, but it's not unusual for us to spill amino acids. So if you eat a really heavy-duty protein-rich meal, you will probably have some amino acids in your urine. If you push your threshold up to 65 milligrams per deciliter of amino acids. We can reabsorb sugar better than we can reabsorb amino acids, so it has a lower threshold there. I want to skip that too. Okay, let's talk now about concentrating urine. And the way this works is in the juxtamedullary nephrons. Remember, only about 15% of our nephrons are juxtamedullaries, but these are really important for concentrating our urine. They are very long. They go way down to the bottom of the medulla, almost down to the papillae, and come back up. They extend deep down into the renal pyramids, as it says there, and they function to help us water conserve. To talk about concentrating urine, we have to talk a little bit more about osmolarity. You guys just told me that the normal blood osmolarity is about 300 milliosmoles per liter, and that's true. So the number of, depends on the number of solute particles per liter. It's how much stuff is dissolved in that fluid. We can measure it in milliequivalents per liter. So if you dump in a mole of NaCl, you've dumped in 2 moles of ions, right? Because you've dumped in a mole of sodium and you've dumped in a mole of chloride. You've dumped in a mole of positive ions and a mole of negative ions, right? As far as reabsorption and secretion, we've talked about that. Reabsorption is just pulling things back out. Secretion is injecting things in. We don't want any undesirable solutes. Both of them occur in every segment of the nephron except in the corpuscle, but the relative importance changes from segment to segment. Let's talk about the nephron loop and this countercurrent multiplication. What does countercurrent multiplication mean? Countercurrent exchange. Well, what happens is you've got fluid coming down and you've got fluid going up. And it's an exchange that occurs between these parallel loops, okay? And by doing it this way, we can get our fluids very concentrated. The countercurrent refers to the fact that the fluids are moving in opposite directions. These are going down, these are coming up. It's called multiplication because as this is getting more concentrated, more concentrated, more concentrated, this is getting less concentrated, less concentrated, less concentrating. But by doing that, it becomes super concentrated down here at the bottom. Multiplication refers to the effect of this exchange back and forth. Remember that the 2 loops are very close together. They're separated by just by a little bit of peritubular fluid out in the middle here. And remember that they have different permeability concentrations. I'd like to slip through this just a bit and go into these slides here. Okay, here's what countercurrent multiplication really looks like. Let's just say that we have this is our loop of Henle, and this is just the starting system. And it's 300, 300, 300, all the way around 300, okay? And then we have a series of pumps that pump the sodium and the chloride from one side to the other, okay? But they can only pump it to a concentration 200 different, okay? So the pumps turn on, and the pumps pump it in this direction, and so the concentration on this side now is 400, concentration on this side is 200. But we got to get it a lot more concentrated than that. So each time we're going to do this, and we're doing this in a real slow progression just to try to make the point to you. Each time we shift it, we put some more fluid in here, but the fluid coming into the system is always going to be 300, which is normal, right? And then we're going to pump until we have a 200 different each time. So we're going to move it, we're going to pump it, and then we're going to shift the fluid around through the tube a little bit more. So we pump it again. And now this one becomes 150, and that's 350. This one becomes 200. This one becomes 400, because we're pumping 200 in that direction. Let's add more. Put in another bunch of 300 up here. Move all the others around. And now let's pump it again. 200 to 300 is going to become 150 to 350, because it's going to establish that 200 difference again. Get that? So now it's 150, 200, 175. Wait a minute. It's getting more concentrated. It's up to 550. We didn't have the ability to pump anything that concentrated. Let's do it again. 450, 550, let's roll it again, 600. Still, by just pumping 200 different, we've got it built up to 600 down here. Let's do it again, 631. Now, why does it work that way? Well, it works that way because these are constantly getting more concentrated, right? These are getting less concentrated, but as they continue to move, it gets more and more concentrated down in this area, okay? That is countercurrent multiplication. That's how it works. Let's go a little bit more, and let's just say we've done it a bunch more steps, and this is actually where it ends up. It actually ends up being 1200 down here at the bottom. It becomes very concentrated. So at the tips of those pyramids in your kidney, down at the bottom, it is very, very concentrated with sodium chloride. Now why, but you see that then as it comes back up, it goes right back to normal, all the way back to 1 again, or 100. So what's the big deal? Well, the big deal is this. The next two slides explain the whole answer to you here. So we've got it coming in at 300, it gets up to 1200, goes back up, and it's coming back to 100, and then what happens? Well, let's just say we have some ADH available, okay? ADH is antidiuretic hormone, right? And in the presence of antidiuretic hormone, we can, well, this is the presence of ADH. This is absence of ADH. Let's talk about this one first. With no ADH, what happens? Well, as the water comes up here, then it's going to make one last trip down through the renal papillae, down through the collecting duct, okay? And you notice with no ADH present, it just kind of flows on because none of the water is reabsorbed. And sure enough, we're making very large quantities of very dilute urine. So that's the patient in the ICU that had the damage to their pituitary gland, their posterior pituitary, they're not making any ADH, and they're peeing out lots and lots of very dilute urine, and they can't stop, okay? On the other hand, if it's a normal patient and they have some ADH, then what happens? Well, the ADH causes the opening of these little doors along here. We call them aquapores. They're water pores that under the presence of the ADH, it comes back down here. And why does the water rush out so fast? The water comes out very fast to make this very, very concentrated. The reason it does is because this whole area down here in the bottom part of the loop of Henle has also become very concentrated. It's 1200 down here. 1200, 1200, 1200, 1200, 1200, 1200. When it's 1200 in there, what does the water want to do? wants to get out of there, and the water just pours out through those aquipores, and we lose a little water. We're now making very concentrated urine, and that's what we really want to do, is make concentrated urine. So the whole idea of the multiplication, the counter multiplication, is to set up this system in the pointy parts of your kidney that are very dilute up at the top and very concentrated down at the bottom. By having that gradient set up where it's very concentrated down here, and it's concentrated down here, the water pours out trying to dilute it. What are the benefits of this system? Well, it's an easy way to reabsorb all this water. Establishing this concentration gradient, it works. It doesn't require a bunch of energy to do this. It just works by osmosis and some pumping. I'm going to stop. We're almost to the end. Okay, so just in summary today, we started talking about filtration and all the controls on filtration, because indeed many of the body's controls of urine output are based on the body's control of filtration and how much filtrate we make. We talked about the different ways we can control the amount of filtration, and then from there it goes down the loop and back up the loop. As it does that, it's filtering it, it's pulling out things, and that's called reabsorption. It's pushing in things, that's called secretion. Works its way around, comes back by the juxtaglomerular complex up there, which is like one more last read on it to see how concentrated it is, so that we can adjust the amount of blood flowing in at the A and out at the E. And then in the process, it creates the very concentrated region down in the distal, in the central parts of the medulla, to allow us to get rid of all that extra fluid, get the fluid out of the urine and back into our system. Okay, we'll go over that test here in a few minutes. Everybody has a grade. Let's take just a minute. Somebody got a schedule on them? Can I look at your schedule there? So according to this, we're supposed to have the lecture exam the week of the 15th and the lab exam the week of the 15th. And this is, that's next week. Let's make it the next week. We'll move it back a day or two. We'll make it on Thursday of the next week. We'll put both exams on the same day. So that will be on
The 25th.
the 25th, right. Thursday the 25th will be our next practical and our next written. Is that okay?
Yes.
All right. I can also tell you that our second final, second midterm will be the 25th, we said?
Yeah.
And the last one, our final exam, will be on Tuesday of final exam week.
So March 25th will be the second?
No,
Or
February
sorry,
25th.
Okay, and then.
The 15th?
No, the week of the 15th, so it'll be on Tuesday, so it'll be the 16th.
No,
Tuesday the 15th.
Tuesday the 15th.
You sure?
I'm looking at my calendar. On there it says
Are you looking at
On
March?
here it says 15th, yeah.
Well, you wrote the right day.
I didn't do it.
Well.
Tuesday the 15th. Okay.
Unless you're the only right one and everybody else is wrong. It's a leap year this year, that's why.
Oh, that's right. So
Moves everything back.
let's all go tell Dr. Cruz. This is a leap year. You screwed up all the schedules, guy.
You can tell him that.
Yeah, I will. So this will be both the practical and the written.
And then we're all gonna go drink afterwards.
That'd be fine.
And then Dr. Sessions, you said that, for the one on the 25th, it was gonna be
It's gonna be both.
some of the questions were gonna be the essay questions.
Right.
When we get those.
Yeah.
I'll have those out for you today
Okay.
online.
I appreciate it.
So we can start working on.
There's already a set up there, and they'll be pretty close to those, if not the same.